So chapter 5 is all about molecules and compounds. And so what we're going to do in this first 15 minutes or so today is we're going to kind of establish some of the differences between the different kinds of molecules that we will name. And then we'll spend Wednesday and Friday talking about how to name each of those different groups. So let's start off with some basics here. By definition, we know that a compound has a constant composition. That's what makes it a compound. Remember, it's a pure substance. So every element in that compound exists. It will always exist at that fixed ratio of one thing to another. Let me pause here for a second. It just occurred to me that none of you can see this unless I open up Pear Deck. So if you have been following along with the Pear Deck presentation as we've been talking about it, go ahead and I'm not going to take attendance again. So if you don't use it for anything other than that, you don't have to log in again. But if you do follow along, this will allow you to follow along. So as I was saying, we know by definition that compounds are pure substances. They always have the same elements in the same proportion, the same way every single time. All that a chemical formula is just a symbolic way of representing what that substance is. So a chemical formula tells us how many different elements are in a given compound and what those elements are and what proportion each of them are in. That's what a chemical formula does. Now, by convention, that chemical formula is going to show us through a series of letters and numbers what is present. So if we take water, for example, water is H2O. That chemical formula tells us that there are 2 hydrogen atoms in that water molecule and that there is 1 oxygen atom in that water molecule. By convention, if we have only one of a particular element, we don't use the subscript of 1. We just assume that if there is no subscript number associated with an element, that means that there's only one of that atom, one of that element in that compound. So again, H2O, the 2 here tells us we have 2 hydrogens. The lack of a subscript there tells us we only have 1 hydrogen. Or excuse me, that we only have 1 oxygen. Another important thing to know about chemical formulas. If I change the subscripts, it completely changes the nature of the compound. So take, for example, I've got 2 compounds here that contain carbon and oxygen. One is carbon dioxide, CO2. This is a common byproduct of our respiration process. It's also a common byproduct of complete combustion. When things burn and burn efficiently, carbon dioxide is one of the byproducts of that reaction. Completely different in chemical appearance, chemical identity, chemical properties to carbon monoxide. Carbon monoxide is not something that we produce in our bodies naturally. In fact, if we did, we would be responsible for our own suffocation. Carbon dioxide is not something that you want a terribly large amount of in your body. Can contribute to acidosis and some other nasty kinds of side effects in your body. But Your body has a way of expelling it relatively easily. We call it breathing. Carbon monoxide, on the other hand, binds to your hemoglobin and basically destroys the hemoglobin receptor for oxygen, and that's how you can suffocate from it. The difference between them is one oxygen. So identity of a compound is very much related to its physical properties and its chemical properties. And changing that identity, changing that ratio of one element to another can drastically change the overall properties of the substance itself. A couple of other notes that you should consider. Order. The order of elemental presentation in a compound does matter. And the general convention is this. When we list out a chemical formula, we are going to list out the elements in that formula from metallic to least metallic. So the most metallic element, that's going to be the one that is the leftmost in the compound. The least metallic element is going to be the one that is the rightmost in the compound. This is why when we describe things like table salt, sodium chloride, we always write it as NaCl. You never see it written as ClNa. That's the convention. Sodium is the metallic component, chlorine is the non-metallic component. We always put the metallic component first. And this is true for ionic compounds like these. It's also true for non-metallic compounds. So taking, for example, nitrogen dioxide, NO2. Why is the nitrogen listed first? Because the nitrogen is the more metallic element. How do I know what order to go in? Usually pretty easy. The further to the left of the periodic table we are, the more metallic it is. Now, up and down, metallic nature, generally speaking, as you go down the periodic table, things get more metallic as well. So if I have sodium and potassium in the same compound, the potassium is more metallic, it would get listed first. We've made some allusions to this in the past, but we're going to state it more explicitly now. Elements can exist both as atomic and as molecular kinds of compounds. So how do I know which one is which? So the atomic elements, these are the ones that tend to exist as singular atoms. And for the most part, most elements fit into this category. This includes all of your metals. Your metals exist as these atomic elements. Now, when we get into bonding, we'll talk about how atoms of metals can kind of bind themselves to each other into this large 3D array. But each one of those dots in that array is an individual atom of that element. Most elements exist in this way. Atomic. Individual atoms, maybe they're loosely associated with each other when they make solids and liquids, but for the most part, they're individual atoms. Molecular elements, on the other hand, some of them do exist quite commonly. When they do, there's usually a reason behind it. I made mention of what are called diatomic elements in the past couple of lectures. In particular, I talked about the halogens existing in this kind of way. Halogens are so reactive that they react with themselves if there's nothing else to react with. That's an example of a diatomic molecule, where I've got two fluorine atoms that instead of existing as atoms, they link up together to make a fluorine molecule, F2. Where do these exist? Again, for atomic elements, this is most of them. And so if they are in the liquid or gas state, they kind of look like this at the atomic level, where you've got a whole bunch of them near each other, but they're not actually bonded to each other in any kind of chemical way. They're physically close, but they're not chemically bound. Molecular elements, on the other hand, you can see the difference. Notice that instead of individual atoms, we see clusters of diatoms, two atoms together in that sample of fluorine, two atoms together in a sample of liquid bromine, two atoms together in a kind of compressed way in a sample of solid iodine. This is our list of elements that exist as diatomic. So, not surprising at all, talk about the halogens exhibiting this kind of behavior. Halogens are on that list. Every single one of the halogens exhibits diatomic behavior. Also on this list are the most reactive of the nonmetals. So we're talking about oxygen. We know oxygen is very reactive because we know that it injects itself into a lot of different, it's what metals react with when metals are reacting with the air. Nitrogen, also relatively reactive. It only exists as N2 naturally. Hydrogen. Hydrogen is shown here as the kind of the top of the alkali metals, even though it's not metallic itself. We've never been able to isolate hydrogen long enough to keep it in the metal state or in the solid state to know if it actually exhibits metallic properties or not. But the reason it is there is because it does exhibit similar kinds of properties to the alkali metals in terms of its reaction with nonmetals. But it exists as a diatomic molecule as well. So that's the first kind of sub-classification that we look at when we're starting to think about things coming together. The other sub-classification that we start to look at is how do we sub-classify compounds? So we know compounds are pure substances. Where are there ways that we can break them into groups to help try to make sense of one versus another? And the answer there is yes. We can look at compounds from whether they are molecular or ionic. And when it comes to nomenclature, which we're going to talk about Wednesday and Friday, we're going to look at each of these individually. And so ionic compounds come from the attraction of ions. So we talked about the idea of cations and anions, positive ions and negative ions. The attraction of those positives to negatives, that's what creates these ionic compounds. In most cases, what we can look for from an atomic standpoint is a metal and a nonmetal or a series of nonmetals. That's what ionic compounds tend to look like. There's usually a metallic component and a non-metallic component. Molecular compounds, on the other hand, we usually see these when nonmetals come together. When nonmetals come together, they tend to form molecular compounds instead. And so one of the things that we will start to focus on starting on Wednesday is if I am given a compound formula, I should be able to slot it pretty easily into one of these two subcategories based upon what is in it. If it's just non-metallic elements, I know it's molecular. I can start thinking about naming it as a molecular compound. If it has a metal in it, I know it's ionic. I'm going to treat it as an ionic compound. There's a different naming system for that. And so this is where we will stop. And on Wednesday, we will pick this up and talk about ionic compounds exclusively. And we'll get into how to recognize them, how to name them, and how to go backwards and turn a compound into a name or a name into a compound. So that's what Wednesday is going to be all about. Have a good day. I'll see you on Wednesday.